All right, welcome to another exciting episode of AP Chemistry here at Spain Park High School. Today is Wednesday, March the 1st. Today is March the 1st, wow. Okay. And once again, if you're enjoying these exciting videos, feel free to subscribe to my channel and hit that like button. All right. I have broken 100. Okay. So yesterday we were looking at the practice. We saw the 1988, and then we looked at the 2008B that was identical to it in every way, shape, or form. So today I want us to look at some of the AP problems that are similar to that are more recent. So I want to go all the way back to and I gotta find it. Oh, it's not even on. So while it's warming up, I'll pull it up over here. Last year's exam. Remember how I said that okay. So remember how I said that the three ways in which we, hey listen now, come on, refocus, here we go. All right, so there are three ways we have to calculate the value of K giving concentration data. Number one, they give you everything, and I said you'll never see that. Well, here's last year's exam, okay? The reaction, now this is part F. So and we'll go back and look at A, B, C, D, E, up to this point. But it says the reaction represented by the equation is allowed to achieve equilibrium at a different temperature. The following data gives the following table gives the partial pressures of each species in the equilibrium mixture. So how would we do this? It says use the information to calculate the value of the equilibrium constant Kp at the new temperature. How would we do that? Arin, go ahead. You're saying it to yourself. Go ahead, just say it out loud.
No, that's okay.
You were right. You know how to do it.
Was I?
Yes.
Like, it would be the 4.2 times 2 times 8.4 over 2.7.
That's right, but it's not going to be just 8.4 because what's my Kp expression going to be?
Coefficients becoming exponent.
Okay, so Sage, tell me what I'm going to write.
You're gonna write H2.
No, just the, okay,
Oh, okay, sorry.
I just want the expression.
4.2.
Just the expression, so,
You had it right there.
well, but it's P, the pressure of CO times the pressure of H2, but what? Squared, divided by
PC.
the pressure of the methanol. Okay? So now this particular question does not ask for the actual equilibrium expression, but if it did, write the equilibrium expression, that's all you would write. But this is what Arin was saying, now you just plug in the values. The values are already given. This is the easiest of all types. I mean, AP's getting soft. And so it's going here, so it's going to be 4.2 times 8.4, but it's going to be squared divided by the 2.7, and somebody get me an answer. You can do it one-handed?
Wait. 106. 110.
110?
Isn't it 2 sig
It would be 2 sig figs.
Yeah, 110.
Are we agreeing at 110? Okay? So, hey, that right there should be easy money. Easy money. Right, it's just a straight up equilibrium. They give you the equilibrium concentrations. You just got to plug it in. All right? Now that's probably a 1. I don't know if it only goes to F. What this was 20, so I mean, now, there is a G, but we don't know how to answer G yet. G was a very hard question, as a matter of fact. But let's go back up and look. Oh, there's the expression for the equilibrium Kp. Okay, so that was 1 point right there, just be able to do that. And then F is probably another point. So 2 easy points for sure. This might even be 2 point. Now, I can go back and look at G, A, B, C, D, E, F, G. So there's probably only a couple of 2-pointers in there because it's all worth 10. All right, so if we go here and look, but here, the following particle level, this is just kind of flashing back. This is a little bit of a review. Here's a particle level diagram, shows representative sample of the I cannot read or write, speak. I can't do anything today. Equilibrium mixture represented by the equation given. Now the equation, it's at the top. Here's the equation at the top. So we're going to always go by this one. CH3OH goes to CO plus 2H2. Okay, so that's the equation you're going to be operating with on all these. So if I'm just working backwards. So I have this representation. So here's an equilibrium mixture. It says that the total pressure inside here is 12 atmospheres. What's the pressure of the CO? Take a minute, take 2 minutes. How do you think you would find that? You have the picture, and the total pressure is 12 atmospheres. We want the pressure of the CO. Hold on, let's just let everybody think about it for a minute. Don't say an answer out. Okay, anybody, Jace, you want to venture a guess? Go ahead.
Use the total pressure equals the pressure pressures and use PV equals nRT.
Okay, but do we know the temperature? Do we know the volume? No, it'd be nice if we could use PV equals nRT, but I don't have enough information to use that one. Okay, that would be my first instinct. Kaylee?
Find the ratio of CO to the total number of molecules.
There you go, because what causes pressure? Collisions. Whichever one has the most number of molecules has the most number of collisions, which is going to exert the greatest part of the pressure. Correct? So Kaylee, keep going. So how many COs do we have?
There are 3 CO.
1, 2, 3. How many particles total are there?
I think 10.
So 3 out of 10 are CO. So what does that mean about the pressure? So 30% of the pressure is due to CO because 3 out of the 10 molecules are CO. So the total pressure is 12. So 30% of 12, mental math. No, it's not 4. It's 3. 12 times 3 is 36. 3.6. Okay? So the pressure, the particulate diagram, the pressure is simply the mole fraction. This is called mole fraction or the percent because it's all about collisions. So whichever one has the most number of molecules. So we could do the same thing. This is your hydrogen, 1, 2, 3, 4, 5, 6. So what would the pressure do to the hydrogen be? 7.2. Good math, okay? I like that, okay? So it'd be 6 times 12. 7.2. Then the rest of it is going to be due to the methanol. Okay? Is that outside? Is that? All right. So I really wasn't planning on doing this. I did it in 5th period. But I got sucked into these problems, just kind of going back and just kind of reviewing and just saying, I want you to see how doable these problems are, okay? That, yeah, it's AP Chemistry. Now, let's come back up here to the top. Are hydrogen atoms oxidized or are they reduced? Do not say an answer out. And how would we know? Think about it, 1 minute. Now the hydrogen atoms in this equation, oxidized or reduced? Well, you gotta justify in terms of oxidation numbers. So you can't just guess.
50-50
Okay, so now let's review. What does oxidation and reduction mean? Oxidation is loss of electrons. Reduction is gain of electrons. What happens to the charge if it's reduced? It's reduced. Okay, that's why we call it reduction, because the charge is reduced. So, what's the oxidation state of hydrogen here? In its natural state?
0.
0. We got to make sure we know that. Elements in their natural state are not charged. Oxidation state only applies to when they're combined in a compound. So it's 0 here. What is it always when it combines? +1. So what does that mean? It's going from +1 to 0. Is the charge going up or down? So it's being reduced. Because the oxidation state is changing from +1 to 0. You need to know that. This again should be easy money question. This should be a 10-second question. Okay? We know how to calculate oxidation states. They all add up to 0. But oxygen's -2, hydrogen's +1. Elements in their natural state are going to be 0. Carbon here would be +2. Carbon here is going to be +4. Okay? So, that's an easy one. But it just asks for the hydrogen on that. So now, this one was a little bit trickier. Just complete the Lewis dot structure using the octet rule. Again, just in your notes right there. How would you do this? How would you complete the Lewis dot structure? They tell you that they just want to obey the octet rule. Okay, we're just do it. This one's not a typical one. Your organization on your notes, you was gonna write it down just on whatever happens to open up first. You gotta be able to go back and look at that one easy. So what's the first step in writing a Lewis dot structure? Total number of electrons. 4 plus 6 is 10 electrons. Okay? Draw a single bond between the two. Put my electrons around. That's 2, 4, 6, 8, 10. Now, if you put them around the carbon first, that's 100% fine. It won't matter. But we want to obey the octet rule, so what do we have to do? You got to get carbon up to 8. We got to steal from the rich, share with the poor. What's the rich? Oxygen. So, if I do that, 2, 4, 6, okay, I have to do that, now I get 8. It's a triple bond. Now you say, but oxygen can't form a triple bond. Well, it normally doesn't, but in this case it does, and the only way you can make the octet rule is to do the triple bond. Okay? Again, very doable. Right? Count the total number of electrons. Put your extra electrons around the outside. Steal from the rich, share with the poor until you get everything having 8. All right? So far, very doable. Now, come back to your favorite. The values of standard molar entropies of the compounds involved in the reaction are given. So here's my reaction again. Okay? Use the data to calculate the standard entropy change in joules per K moles for the reaction. How would you do, again, just do it. How would we do this? This is last unit, thermochemistry. Don't say it, just do it. Just do it, just like Nike. Just do it.
What are you looking at? Yes.
Again, you would have your equation sheet, and the equation you need would be on the equation sheet.
You didn't say.
We do not need delta H for this part. But there's one other equation for delta S. That's one of the equations for delta S. That equation is actually coming up, but there's a second equation. The delta S, delta H, delta G all have the same equation. Come on, y'all. Delta S of the reaction is equal to the sum of delta S of products minus the sum of your delta S of reactants. And it's actually not delta S, it's S of formation, S. This is the one thing that's not a change. You have the absolute entropies. So it's products minus reactants. Okay? Now this is on the equation sheet, but you just got to know that if I'm going to find entropy, and I want the entropy of the reaction. Sometimes they may give you, that they might give you this delta S value and leave one of these and just put a question mark. And say calculate the absolute entropy of the hydrogen. But in this case, they gave you everything, so what do we plug in? Delta S of the reaction is going to equal what? Okay? Products minus reactants, so it's going to be 198 plus what? 2 times 131 minus 240. What's that going to equal? 220? Okay? And that's joules. Okay? Joules per K, actually. Joules per K. Moles cancel out because you multiply by coefficients, cancel moles. All right? Again, not super heavy duty math. You just got to know what to do. Since we're just given entropy, we're not going to use the delta G equation. We're going to use the other entropy equation. But delta S, delta H, delta G are all products minus reactants. You calculate them all that way. Delta S comes out in joules. The other two come out in kilojoules. So we got that. Okay? So remember the 220. So then we come down. We're on CI. Here's CI2. So calculate delta G. Now, we'll come back up here. So calculate delta G. That's given. So we know this. So delta H is equal to a positive 90 kilojoules per mole reaction. We just got delta S to equal 220 joules per K. So, Otto, you did so well for the first 5 minutes.
I made it 20.
No? What's the degree symbol mean? Standard, so what's the temperature? Oh, come on. 25 degrees Celsius, 298 K. No, but actually they're telling you here, what's delta G? They're telling you the temperature here though. All right, there's really only one trick. There's only one trick, one thing you got to pay attention to on this. Because delta G is going to equal delta H minus T delta S. Now, because it's just T, it always has to be Kelvin, but it's given Kelvin. Okay? So delta H is 90 kilojoules per mole reaction minus 375 K times, what do we have to do to the 220? I just heard a moment. Say what? Convert to kilojoules by dividing by 1,000 because they have to be in the same unit. The mistake that people make is that they don't convert this, that they don't make the units match. So it's going to be 0.220. Okay, and this is K, and that's kilojoules now per K. So the K's cancel, and this mole reaction isn't really even a unit. So 90 minus. You just always got to throw this in there because it doesn't really. It's a made-up unit. 7.5. Oh, I seen a bunch of head shaking. So 7.5 kilojoules, since they tell you, per mole reaction. All right. So again. No in-depth heavy-duty math. You just have to, as long as you just know what to do. When you have delta H and delta S, you can use this equation. But if we were just given delta S in the previous one, you've got to do products minus reactants. So we've gone through and done this whole question, except the last one. The last one's a hard one. We haven't gotten to that part of this unit yet. Okay? But we can just say now we've looked at this whole question, beginning question 2, a 10-point question. There's nothing on here that we haven't talked about or don't know how to do until we get down here to G. And we'll hit that. What's today? Today's Wednesday. Probably won't do it tomorrow, but probably on Friday. Okay? So that is all. Just again. Write the electron configuration for aluminum. Why is Al plus 3 smaller? Well, how do you make an ion? How do you make a positive ion? You lose the valence electrons, right? So it's got one less valence shell. So it's smaller, okay? Now, we're not going to keep going down there. I'll stay here all day. Okay, so, oh, there it is up there. 2017. I think, do I already have it pulled? Well, let's just kind of scroll through 2017. And again, these are all just available to you. I'm just on the website. Okay? This one here is synthesized chemistry runs the reaction. This is a stoichiometry of gas law. How many moles? That's PV equals nRT. Okay, but you ask the question, explain how I just as I go through here. The reaction is thermodynamically favorable, but no reaction is observed to occur. What's the reason why always? The reaction has a high activation energy, right? Whenever it says that it's thermodynamically favorable, but it doesn't occur at observable amount, that means that it has a high activation energy. So the reaction occurs at 120. Why does the higher temperature, how does it affect the collisions between the reactant molecules that the reaction occurs at an observable rate? Okay, but what's for temperature? Not necessarily the number of collisions. Okay, they have to overcome the energy of activation. Okay, collision frequency, that's the concentration. Yeah, temperature does that, but this is talking about the temperature and the energy of activation. So they're going to collide with more energy, so more molecules at the higher temperature, more molecules have enough energy to overcome EA. All right, so we have two criteria for an effective collision, but when it's dealing with temperature, it's going to be EA. Now, in your mind's eye, do not say an answer out. The graph below shows the distribution of collisions at 120. Draw a second curve on the graph that shows the distribution at 30. Don't say an answer out. What would it look like at 30? Now this is the graph again at 120. This is the graph at 120. It wants the graph at 30. Okay? I'm seeing a lot of people doing to the right. Okay? But is the temperature higher or lower?
Lower.
So what does that mean? It's going to be left and higher. Remember, it shifts lower, so when I'm looking at, here's my activation energy at the lower temperature, why doesn't it occur? Because very few molecules make it past here. It's going to be more like that. So only a very few molecules would have enough energy to overcome EA. The lower temperature is going to be higher and to the left. This Maxwell-Boltzmann temperature distribution graph shows up all the time. Know it forwards and backwards. Everybody wants to go like this just because the second one's always lower, and to the right. But you got to look at your temperatures. Okay? Read the question carefully. Haven't even gotten to the question I'm looking for yet. I just can't help myself. It's good stuff. The year in review so far. Okay. All right, so here's another Lewis dot structure. I want you to do this one. These should be easy money. This should be automatic. You say, yes, thank you, Lord. It's a good review, right? There's so many different ways that organic molecules can combine together. That at least look at your structure. It's been a long time coming. Good. Good. Yeah, my wife always said when she was there, she goes, yeah, let them do that too much and We have it? Don't make it complicated. How many electrons do we have? 26. Okay? So 26 electrons, step one. Put my single bonds. So that's 2, 4, 6. Just start on the outside. 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. If it ain't broke, don't fix it. Hey, we've got to be able to, I mean, that's just easy. That's low-lying fruit, as they say. It's just right there, easy to grab. Easy money. Okay, now, what's the approximate value of the chlorine? What's the approximate value then of that bond angle, with this being my central atom? Okay? How many electron pair domains do we have around the sulfur? The central atom is what we always look at. How many electron pair domains? 4. 2 bonding, 2 lone pair. So 4 pair of electrons are always in what shape? Tetrahedral. We have to know those bond and so what's the bond angle of a tetrahedral? See, you're starting on it right. That's not 120, that's trigonal planar. 0.5. Okay, but so it's 109.5, and if you put 109.5, you probably got credit for it. But the reality is we got 2 lone pair. What do the lone pair do?
Distort it. Like more gas. Like they take up more space.
They take up more space, so what does that do to the bonding pairs? Bonding angles. Make it smaller, 2 to 3 degrees per lone pair. So we can say approximately 105. Now I think on this year they took anywhere from 100 to 110 as an answer. Okay? But the reality is it's going to be somewhere around 105. Now it's going to vary molecule to molecules, approximately 2 to 3 per lone pair. So approximately 105, anything in there. Slightly less than 109.5. But that's why we have to know our bond angles in there. So that one's a little bit tougher. Okay? I'm making my way to the problem I want. What do I have to 52, right? Okay. So now it says, so here's this. Identify all the types of intermolecular forces in HCl. They all have what? I know, now I'm asked, but LDFs. So we know we list LDFs. Now, do I have to explain anything?
No, just said it.
I just list. LDFs for sure. Phone call. What does that mean? Not hydrogen bonding, phone call. Dipole-dipole. Does it have hydrogen bonding? No, because only phone. Only phone for hydrogen. So you just list those 2. London dispersion, dipole-dipole. Now don't say an answer out. Okay? Here, the CCl4 condenses at 70 degrees. The HCl remains a gas. What does it mean, first off, to condense? You're allowed to answer that. Turns into a liquid. So it sticks together. Versus the HCl doesn't stick together. So what can be inferred about the relative strengths of the IMFs between CCl4 and HCl? Which one's stronger? CCl4. Now, CCl4 is nonpolar, so what's the only type of IMF? LDFs. But because it's way bigger, the LDFs of CCl4 are stronger than the combined LDFs and dipole-dipole of HCl. Because it condenses first. Again, I look at this without this information here, I'm going to say that this one's got dipole-dipole, so it's going to be stronger. But it tells me it condenses beforehand. I got to go with the data. Okay? The higher the boiling point. The one that condenses first is always going to have the stronger attractive forces. All right, we've already done that one. We already did that one. Okay, just real quick, we're not going to do this, but if it says bond enthalpy or bond energy, what equation do we use? Okay, broken minus formed, reactants minus products. Okay, so you just plug in. You just count all your bonds. It's reactants minus products. That's the one that's backwards. That's the one that's not on your equation sheet. All right? Now, this is the question that I was thinking about for last one. Okay? It tells me that it's first order. How does this data support the fact that the rate is first order? 30 seconds, think about it. Okay? Okay, but they don't give you that, do they? There's no way they're asking you to plot all this. Okay, you're warm. Okay, Jace?
It's non-linear.
Okay, you gotta speak up. You got that mask on.
It's non-linear and it's decreasing, so when I, so it's decreasing.
No, we need a little bit more than that.
The half-life stays constant.
How do you know the half-life stays constant?
Because it takes the same amount of time. Yeah.
Okay, that's half to half to half, 10 to 10 to 10, right? So the half-life stays constant, so therefore that's an indication that it's a first order reaction. That confirms that it's a first order. That agrees with that it's first order. Now, how do I find my rate constant K then if it's first order? Now this is on your equation sheet. Over K, so K is going to equal 0.693 over T1 half over 10, so K is going to equal 0.0693 per hour. You got to have the unit, 1 point for the unit. Okay? Again, yeah, I don't need to be in. Again, very doable. But this is the one I was trying to remember, that I remember seeing as far as the half-life was concerned. Okay? So you just have to know, half-life stays constant, confirms first order. Hopefully that'll stick. All right, come on, equilibrium. All right, here we go. 3A and B, we're gonna end the day, 3A and B. They actually got to the equilibrium question. Three A and B. ACT we do on 14. She just got to go through the training on that. We're gonna talk fast and I'm gonna have to research. I gotta get the alabaster fiber with nitrogen for tomorrow. Unfortunately, I'm a little counting on him. He's usually ahead of me. And this time of day, the traffic. And they close at 4:30. They love it when it's coming in at 4:20. Well, next time, hey, where do you have to be right now? Haven't had to do it back.
Please do.
Now, just one of the common mistakes is that it's asking for KP, but students instinctively sometimes do it in terms of KC with the brackets. So you just got to make sure that if it's asking for KP or KC, to put it in the proper form, okay? Because that would be, again, a careless miss. So just make sure you read. So KP is going to be the pressure of the NO squared pressure of the N2, pressure of the O2. So that's 1 point. Okay? 1 point. .61. All right, we're running out of time, so hopefully you at least have a plan. Ice, Ice Baby. I still haven't ever played it for you. Okay? So what does it tell me at equilibrium?
At equilibrium, you have a 0.122 atmospheres of NO2.
122 of the NO. Correct? So, what does that make my change over here?
0, 0,
Minus 0.061. Why 61, not 122? For every 2, you only have 1, so it's going to be a half. So it's minus 0.061. So at equilibrium, what is my value? 5.95. And this can be
1.55.
4.5?
55.
5.5. Okay? Now, once we have this, we plug and chug into here. So Kp is going to equal my NO, the 0.122 squared, over 5.95 times 1.55. This is the type of problem, again, that we're just working on in this unit. This is the second type of the 3. And the answer turns out to equal
1.62 times 10 to the negative.
okay, what did we get, Zach?
1.62 times 10 to the negative third.
Times 10 to the minus third, which is the same as 0.00162. Either way you write it. Okay, now hold on a second. Okay, so starting tomorrow, we're going to come in, we have to go the other direction. Now normally there's going to be 4 or 5 different ways we can calculate the value equilibrium certain concentrations given K. Here we're given concentration finding K. Now we're going to go given K, find concentration. But I am going to cut out a lot of them and just kind of do the main ones because I haven't seen problems like it in a long time. Okay? And so we need to make sure that we get to the ones that I know for sure are going to be on the exam.
You're recording tomorrow, right?
Yes, I will record tomorrow. Okay? Lights, camera.